So when you talk about the related rates, now, as I said earlier, that related rates will be linking two different quantities. Like, for example, if I have, let's say, the volume of a cone is given by 4/3 pi r cubed. Now, when I just do dV by dr, this simply means that I'm finding out the rate of change of volume with respect to r. And this is not the related rates. Now, related rates will be something, a context where, let's say, your radius is changing at certain rate with respect to time. Okay, so for example, my radius is increasing or decreasing at certain rate. So, for example, if this is a sphere currently, which is at a radius of 10, now after some point of time, it becomes like a small sphere of radius of 5. So you can see that as volume also change, but progressively it is a link with at what rate radius is changing, and using that you can predict other way, like in other quantities, like at what rate volume is changing with respect to time. So now here the time comes as the third factor. Time comes as the third variable indirectly. So related rates is um, generally with respect to time, with respect to time. In this, they will give us out of the two quantities, they will give us out of indeed like four quantities. Now, for example, volume, radius, rate of change of radius, which is going to be referred as dr by dt, rate of change of radius with respect to time, they might give it, and they might ask us to find out dv by dt. So it's like volume, radius, dr by dt, dv by dt, rate of change of radius with respect to time, rate of change of volume with respect to time. So few of these quantities will be given, and you want to find out at what rate the others are changing and vice versa. So first, let's link up. Let's see how we can link up and introduce time as a variable. Let's try to understand how time can be introduced. So now, okay, I can just find out dv by dr is 4/3 pi times 3r squared. But now here there is no time involved. There is nothing as such time. So we go back and just refer the simple rule out here. So that let's say if I have dv by dt, suppose let's say I want to find out at what rate the volume is changing, at what rate the volume is changing, that can be broken down into two parts. So at what rate your volume is changing with respect to radius times at what rate your radius is changing with respect to time. And it is simple algorithm. In simple lame term, if I say, okay, I can cancel this and this, and still it is dv by dt. So some people tell in that way, but it is linked up with a very interesting fact that rate of change of volume with respect to time will be at how volume is changing with respect to radius times how radius is changing with respect to time. So now what comes is that, is there a way that we can link up or create a shortcut for this particular thing? So let us say, now I'll make the problem more particular. So let's say here the volume of the sphere is given by, the volume of sphere is given by 4/3 pi r cube, where r is the radius of the sphere. And when radius is 3, rate of change of radius is 0.1. Let's say this is in centimeters. The rate of change of radius is 0.1 centimeters per second. So it is, let's say, decreasing at 0.1 centimeter per second. At what rate, volume is changing? At what rate volume is changing in this case then? So now what we'll be doing is dv by dt is something that we have to find out. So this is what I have to find out. So dv by dr, let's see what we get. So dv by dr will be 4/3 times pi times 3r squared. That's your dv by dr times this dr by dt as it is. So don't touch that. Now, since they have given us the radius, like dv by dt will be equals to 4/3 pi times 3 times radius is nothing but 3. So that will be given in the question at what instance you're looking at. So it'll be 3 squared times dr by dt is also given is negative 0.1. So if you calculate this value, this is going to be like, let's say this is gone. So the 9 4s are 36 pi. So negative 3.6 pi. So you can see that every second at that time, the volume will change or volume will reduce by negative 3.6 pi. So at that instant, when radius is 3, and if the rate of change of radius is 0.1, at that time, volume will be reducing by negative 3.6 pi. So now the next part is that when I look at the rate of change of, let's say, one quantity with respect to other, now I personally do it in a particular way where, like, suppose if you have been given a function, let's say g of, let's say, x is, for example, or in simple terms, let's say y equals to f of x, suppose. And when I want to do the rate of change here, so let's say dy by dt will be f dash of x, do normal derivative with respect to x times whichever variable you have been given, just multiply with the derivative of that. So you don't need to do that every time dv by dt is dv by dr times dr by dt. So you can just remember this way. Now, for example, if I have y equals, so let's say there is a function uh, and there is a ball drifting along this, okay, and what we'll be knowing is that, let's say, y equals to x squared plus 4 is the function, and it has been given that the rate of change of x coordinate is 0.1 per second, and you have to find out rate of change of y. What is rate of change of y when x is, let's say, 2? So when you're introducing rate of change here, related rates here, you don't need to really worry about now. Just do dy by dt. So y with respect to t will be dy by dt equals to, now do the normal derivative of this, will be 2x times dx by dt. So this is what I meant to do by that logic. So this is going to be a formula which is going to, you can use it. So dy by dt is going to be then 2 times x is 2 times 0.1, and that's like 4 times 0.1, so it'll be 0.4. So as x changes at 0.1, as x is increasing at 0.1 rate at x equals to 2, the y will be also increasing by 0.4 at that point. So this is something which is important. Now, sometimes you'll get an implicit equation. Now, for implicit, my strategy will be a little different. So like, for example, if I have got volume cube is given by, let's say, 4L cube plus 3R square. Now, sometimes I might link up with 3 variables. How do I tackle the situation in that case? So let's say volume, length, and radius of any particular object. I don't know what this formula is for, but I'm just linking up with how can I link up related rates out here. So when you're doing this particular kind of question, like remember that R and L, these are changing it. Assume that they're all changing. So let's say a unique example is something like this. Suppose there is a cone, which I'm going to come next in a minute. So let's, this is a cone where you're filling up water. So number one is the volume of water is changing at every second. Number two is radius of the surface is changing. And number three is height is also changing. So 3 variables are changing at the same time. So how do we introduce related rates out there? So when you're doing the related rates in case of implicit functions like this, do once again normal derivatives. So suppose if you have a function y to the power n, like how you do normal implicit differentiation. If you're differentiating with respect to time, do the normal derivative n y to the power n minus 1 times dy by dt. So like how we did the normal implicit differentiation, that's how it comes out here. So if you differentiate both the side with respect to t here, with respect to t, what we get is 3v square normal derivative times dv by dt. Similarly, it'll be 12l square dl by dt. equals to 6r dr by dt. I mean, plus 6r dr by dt. So whichever variables you're differentiating, just make sure that you multiply with the derivative of that variable with respect to time. So this is something which is like the key to develop the relation between two different functions, which involves the related rates. So what we'll do is we'll basically take now three examples. Number one, I think, is like basic favorite problem is the ladder problem. Okay, so this is like ladder problem. We're going to take a cone problem. Uh, then we're going to take a problem which is linking up with motion. So we're going to take all these three problems in this particular example. So now in ladder problem is basically generally the situation is given that there is a ladder that is lying against a wall. So this is the, assume this is the ladder that is lying against the wall, and what's happening is that this ladder end is slipping at, let's say, 2 centimeters per second. And what we have to find out is let's say the length of the ladder is, let's say, 5 meters. And what I have to find out is that at what rate this end is slipping down, at what rate this end is coming down at certain given x value. So when x is, let's say, maybe around 50 centimeters. So how do we do this particular problem? Now, first thing that you see is that there is no variable or relation you can see. So you need to assign the variable and relation firstly to the given problem. So like, for example, here I have x, I can take this as y. And now, since they have given that the length of the ladder is 5 meters, we can take x squared plus y squared equals to 5 squared. So that will be always constant. X squared plus y squared is 25. Now, whether this x comes here and this y comes slightly a bit down, because the length of the ladder is always going to be the hypotenuse. So we will always take that as the relation. Now comes the second point. How do I apply the related rates here now? So obviously, when you look at, you just take the derivative with respect to time, both the sides. It's like the derivative of x squared will be 2x dx by dt. Derivative of y squared will be 2y dy by dt equals to 0. So now we need to have, in order to find out, let's say dy by dt, that's the objective. So here dx by dt has been given. Dx by dt is, let's say, 2. I'm not considering the direction of the basic kinematics motion, like taking negative or positive at this stage. So let's say dx by dt has been given as 2. So what I'm going to take is, and also x value has given as 0.5, because be careful, because x has been given as 0.5. Let's say I'm taking x as 100 meters, 100 centimeters. So this value of x at an instance when I have to find related rates is when it is 100 centimeter from the wall. So that helps us in calculation. So if I take x is 1 meter, basically, I can find the y value also. Y is 1 square plus y square is 5 square. So that gives me y square is 24, and will be y is root of 24. So this is nothing but the value of the y when it is at 100 centimeter or 1 meter away from the wall. So next step is to put these values. So when I say 2 times x is 1 meter, dx by dt is basically given as 2, and 2 times y we got is root 24 times dy by dt equals to 0. So we get dy by dt will be equals to negative 4 over 2 times root of 24. So that simplifies to, let's say, negative, this becomes negative 2 upon root 24. You can further simplify this, of course. So that's how you find out the rate of change of y with respect to time. So now consider the case like where second problem is about a cone which is inverted, and water is being filled in this cone at least a 3 centimeter cube per second. And as a result of being water filled, like the water level keep rising. So at an instance, let's say when the radius of this water cone is r and this height is h, you have to find out the rate of change of height, let's say dh by dt, you have to find out when dr by dt is, let's say, 5, when dr by dt is 5, and the radius is, let's say, radius is 3 and height is, let's say, 2 as per given condition. Sometimes like we'll apply similarity and all that, I'll take in a different problem, but like right now we'll just take it very straightforward problem where you have to do the related rates. Now the important thing is that amount of water being filled, like, is, let's say, v is 1/3 pi r square h. That's 1/3 pi r square h. Now here you can see that the three quantities are changing. Radius is changing, I mean the height is changing, and the volume of the cone is changing. So when you want to find the related rates in this case, it's once again boils down to the product rule. So let's say I'm doing the dv by dt equals to 1/3 pi is a constant. Now we'll do radius square derivative times height plus height times derivative radius. So radius square times derivative height. Now height, if you're differentiating with respect to time, obviously it'll be simply dh by dt. If you don't know how to do this, like h raised to 1, I mean h raised to 1. So 1 h raised to 1 minus 1 times dh by dt if you apply the implicit part. So this is very simple. Rate of change of height with respect to time, anybody will say it'll be simply dh by dt. Plus now height as it is times radius square derivative. So times 2r into dr by dt. I repeat again, here we are applying product rule. Radius square is one variable, height is another variable. You're differentiating both of them with respect to time. So radius square times derivative height with respect to time, which is dh by dt, plus height times radius square derivative, which is 2r dr by dt. So this is how you basically set the related rates expression. And now let's say when I take r is 3, so dv by dt is 1/3 pi. Radius, if I take as 3 square times dh by dt, we don't know. So dh by dt, you keep it as it is, plus height we know is 2, radius we know is 3 times dr by dt, which again we know is 5. And also we know dv by dt, which is, let's say, 3. So you can find out at what rate your h, this, like, dh by dt is, I mean h is changing basically. So that you can just make dh by dt the subject. I mean, you can solve for dh by dt because you know everything otherwise.